Chapter 6 is on covalent bonds and molecular forces. Chapter 6, Section 1 focuses on what makes up a covalent bond, which is where electrons are going to be shared between two atoms. A single bond involves one shared pair of electrons. A double bond involves two shared pairs of electrons, while a triple bond involves three shared pairs of electrons. A molecular orbital is where the atomic orbitals are going to overlap. So when you form a molecule, that's the area within this molecular orbital where an electron pair from the bond is most likely to exist. So for instance, in this diagram here of the methane molecule, you've got carbon with the blue electrons here being represented, and then each hydrogen molecule or each hydrogen atom with a red electron showing where they form the covalent bonds. And the bond is formed where their atomic orbitals overlap. So you've got the carbon and the hydrogens overlapping. That's where we're going to find those electron pairs. So that's the molecular orbital. Bond length is the average distance between two bonded atoms, and bonds will form when atoms are at a minimum potential energy. So as they start to come towards one another, they'll reach a point where the energy is at its lowest, and that's where the bond will form. That's where it will be most stable. In terms of bond energy, energy is how much energy is required to break a bond between two atoms and then to pull them apart. Now with these different types of covalent bonds, the singles are going to be the weakest bonds or require the least amount of energy to break. They're also the longest bonds. And then triples are going to be the shortest bonds, but they're also the strongest, so it takes the most energy to split those apart. And doubles would be right in the middle. Electronegativity is another trend that we see across the periodic table. It's the tendency of an atom to attract bonding electrons to itself. And the trend that we see is that electronegativity increases as you go across a period and decreases going down a group. The most electronegative element is fluorine, and that's the one that I usually just try to remember. Its electronegativity is 4.0. And so if you recognize where fluorine is on the table, you'll see that it increases across a period and decreases down a group. We exclude the noble gases from this because they're not going to be generally involved in bonding, so they're not going to be trying to attract bonding electrons to themselves. Electron density basically just means that the more electronegative an element is, the higher electron density it will have. That means that it will pull more electrons closer towards it. In this diagram here, you'll see the aluminum here is in the middle of this molecule with three chlorines that are surrounding it. Now aluminum has these red electrons here, and the green electrons are all for the chlorines. Now, chlorine, if you look on your electronegativity sheet, will tell you that it has a higher electronegativity than aluminum does. So instead of sharing these pairs of bonding electrons equally, the chlorines are going to actually pull them closer to themselves and further away from the aluminum. So the chlorine atoms will be more electron dense than the aluminum would be. With covalent bonding, there are also a couple categories, nonpolar and polar, and those values are represented by an electronegativity difference. So if you have two elements that are bonded together and you look up their electronegativities on the table and subtract the lower value from the higher value, if the difference falls between 0 and 0.5, then that will make it a nonpolar covalent bond, which essentially means that the electrons are going to be shared equally between the two elements. If the difference comes out to a value between 0.6 and 2.1, then that will be a polar covalent bond, and that means that the electrons are still going to be shared, but they're not shared equally. They're going to be closer to the more electronegative element. So in this case, element B would be more electron dense. It would be pulling the electrons closer towards itself. And that's going to allow this partial negative charge on this end that has the more electrons, and this side of the molecule will be partially positive. That's what this Greek delta means, partial positives and partial negatives. An ionic bond, we know electrons are transferred, they're not shared anymore. So anytime you have an electron negativity difference larger than 2.1, that means that it's actually an ionic bond, and the electrons will be completely transferred from the cation to the anion. So in this case, you get a full negative charge for the one that is accepting the electron, and a full positive charge for the element that has gotten rid of the electron. A dipole is another name for a molecule that is polar. So you can have polar bonds, but you can also have polar molecules or nonpolar molecules. When one end of the molecule has a partial negative side and one has a partial positive side, that makes it a polar molecule and therefore a dipole. So for instance, water, the oxygen is more electronegative than the hydrogen. If you do the subtraction problem here for your electronegativity difference, you'll see that this bond would be polar and this bond would be polar. So the oxygen pulls the electrons closer towards itself, and you get this partial negative charge. The hydrogens would then have a partial positive charge. And because of this lopsided arrangement, this will be a polar molecule in addition to just having two polar bonds. If these were both positives, then that would not be a polar molecule. If these were both negatives, it would not be a polar molecule. They have to have opposite charges. And those charges can be represented, again, either with these Greek delta symbols or with the arrows. The arrows point towards the more electronegative element, and you draw a little crosshatch on the line for the more positive side. A dipole moment is just another word for the electronegativity difference. So when you do your subtraction between the elements' electronegativities, that value is called the dipole moment, and that just determines the polarity of the bond. And then once you know the polarities of the bonds, you can find out the polarity of the molecule. And this one here is a carbon dioxide molecule. And though each of these bonds is polar, because both side molecules, both side atoms, the oxygens, are going to be more negative, this overall molecule is not going to be polar itself because there's not an uneven distribution of charge. We don't have one charge on one side and one charge on the other. They're both equal, or they're both the same. And the last thing is just that the larger the dipole moment, the larger the electronegativity difference, the greater the polarity is, and therefore the stronger the bond. So in regards to these three bonds that we've talked about, nonpolar would be the weakest, polar would be the next strongest, and then ionic would be the strongest of all of them.